Next is Chandramouli.
Hi, Alok, can you hear me?
I can hear you, Chandramouli. Raghu, you have to stop sharing.
Yes.
Okay, 1 second. Can you see this?
Yes.
Okay, great.
So, Chandramouli, there is you have around 12 minutes and then a couple of minutes for questions. So I will tell you at 12 minutes are up. 13 minutes are up. Yeah.
Okay, great. So
introduce you, I forgot. So we are very happy to have Chandramouli Chowdhury from International Center for Theoretical Sciences, Bangalore, and he's going to tell us about holography from Wheeler-DeWitt equation.
Okay, all right. Thank you very much for this invitation. Like Alok said, I'm going to talk about the holography from Wheeler-DeWitt equation. This talk is based on this paper, and this work is in collaboration with Victor, Olga, and Suvrat. Victor is a postdoc at ICTS, Olga is a postdoc at Perimeter, and Suvrat is my advisor and a faculty at ICTS. So let me actually start by summarizing the main idea of this talk. So the idea is that in a theory of quantum gravity in ADS, if you have two wave functionals which coincide near the boundary on an infinitesimal time interval, then they coincide everywhere else. Okay. Now wave functionals are objects which are not directly space-time dependent, but are dependent on field configurations. So what I mean by them coinciding near the boundary is this precise relation, which says that if you measure the expectation values of the Hamiltonian operator and some operators which are scattered on the conformal boundary of ADS, and they lie in some thin time band here, and you demand that such expectation values are equal for two different wave functions, say psi1 and psi2, then you must have psi1 equal to psi2. Okay. Now, in order to argue for this, we will not be assuming ADS-CFT by any means. In fact, this is not meant to be a proof of ADS-CFT either, but it's just nice that such a property is already visible within canonical gravity. Okay, so just to set the stage, let me give a toy example so that ideas become a bit clearer. So if you consider two different excitations which look like psi1 and psi2 of this form, where say phi1 is some scalar field and phi2 is another flavored scalar field, and f of r are some smearing functions, and lambda is some perturbation parameter. And just for simplicity, let us consider f of r to be the same smearing function. I'll use this to make a point in the next slide. And say phi1 is the red colored thing and phi2 is the blue colored thing. Then the idea is that if you measure such a correlation function, which involves the Hamiltonian at the boundary, and which is how gravity kicks in, and the boundary values of the scalar field, you end up getting some expression like this. The exact form is not important. But what's important is that there's a procedure by which you can completely recover the function f of r by either measuring this correlator or by measuring this correlator. And you can also show that if you measure some cross correlator, which involves, say, the expectation values of the second field in the state psi1, then you would end up getting 0. And therefore, by measuring such simple correlators in a thin time band on the boundary, one can extract information about the state. Now, this would not be possible in classical GR, and this is why I took the same smearing function, because within classical GR, the thing that you would have been able to measure would be the total energy of the state. Since this is spherically symmetric, the only thing that you would have been able to measure was the total energy, and you would not be able to distinguish between the two flavors. And therefore, this toy example shows how information is delocalized in a theory of quantum gravity in a non-trivial manner. And we will study this in a bit more detail in the upcoming slides. Okay, so let me just spend one more slide in trying to motivate why such things would only work in a theory of gravity and not in some other theories. So for example, you can consider some local quantum field theory like a scalar field theory. And in those theories, you would not be able to distinguish a state psi from another state which looks like some bulk unitary acting on the state by only making boundary measurements. And this is because these bulk unitaries would commute with any boundary operator. In a more mathematical sense, if you measure the expectation value of such boundary operators within the state psi, then this expectation value would be equal to another one, where instead of state psi, you now have U bulk acting on state psi. And such a counterexample would not work in gravity because these commutators are non-zero in gravity. And you can actually cook up similar examples even in gauge theories, where now you can construct your bulk out of some local gauge invariant operator. Let's say you can smear these operators like f mu nu squared. And again, such a counterexample would fail in gravity because you cannot construct local gauge invariant operators. And there's actually a more formal way of saying all of this. And that is by saying that you can construct what are called split states in theories like these bullet points 1 and 2. And these split states are basically those which look identical outside some region, but are different within some region. And such states cannot be constructed in gravity. And in all of this, I want to re-emphasize that in order to really reconstruct information in gravity, you have to allow, you have to do more than just measure the energy of the state. You have to also measure correlation functions involving the energy. This is important because the bulk state in general need not just be an energy eigenstate, but can be superpositions of that. Okay. Okay, so now let me talk about how all of this thing connects with the Wheeler-DeWitt equation. So one point that I had already mentioned before is that in a theory of gravity, the energy can be measured from boundary. This one can think of this statement as an analogous statement in a theory of electromagnetism, where you can measure the charge from the boundary. And this can be easily seen by performing some ADM decomposition and writing down the Hamiltonian. And you end up getting terms of this kind. The exact details of these terms are not important. These guys are actually, these things have a name. And what so happens is that this n and ni are constrained by what are called the primary constraints in the theory, but those impose some very non-trivial secondary constraints in the theory, which are known as the Hamiltonian and the momentum constraints. And these set the bulk part of the Hamiltonian to 0. So these first two terms are really a bulk integral on Smikoshi slice. And you're just eventually left with a boundary term, which is also known as the ADM energy. And I'll give an expression for this later. And therefore, the full Hamiltonian itself is a boundary term. Okay, now quantum mechanically, if you want to discuss what are the allowed states or the allowed wave functionals, then you must impose these constraints on the wave functionals. There are equations you can write down for the primary constraints, but the more interesting ones are the secondary constraints, which basically are these guys. And in this, the first equation is known as the Wheeler-DeWitt equation. And again, these equations are analogous to the Gauss law in electromagnetism, where you can have a pointwise constraint, which looks like del dot E minus the local charge density acting on a wave function equal to 0. Now, such constraints describe the gauge invariance of the wave function, and we will be referring to them as the pointwise constraints, as these are not just constraints at one space-time point, but they're constraints at many, in fact, infinitely many points. And in general, these equations are very hard to solve. And therefore, we will study them perturbatively in kappa, which is related to G Newton. And by perturbatively, what I mean is that you consider that you have some background, which is in our case is the ADS background, and you consider tiny fluctuations over them, and you can similarly expand the constraints. And it's often useful to decompose the fluctuations in terms of some longitudinal and transverse modes, similar to how you would have done in electromagnetism. So in this equation, this first term is the longitudinal mode, and these two guys correspond to the transverse mode, within which this particular term takes care of the trace of the transverse mode, and these take care of the transverse traceless components, which also would correspond to the physical gravitons. These equations just define what these are, but anyway. Okay, now the pointwise constraints are very difficult to solve even in perturbation theory. And in general, what are easier are something called the integrated constraints. And an example of an integrated constraint is again our friendly Gauss law in electromagnetism, which says that if you want to measure the total flux at infinity, or say the boundary of some Cauchy slice, then you can measure the electric field dotted with the surface, the surface area vector, and that would be equal to the total charge inside. And similarly in gravity, the integrated Hamiltonian constraint, which is more important for us, takes the following form, where this H boundary is the same as the ADM energy. And this relates this particular surface integral with some integral over the bulk energy densities, which look like this. So the only important thing in here is that the boundary value of the Hamiltonian only picks up one particular component of the transverse mode, which is the trace of the transverse mode, HT, and yeah, and HL just drops out. Okay, now the solutions of the integrated constraints in general would depend on the transverse traceless component, then the scalar matter. The scalar is not such a important thing. We could have done it for any matter sector. Scalar is just easier to solve, and the boundary value of the Hamiltonian. And we can solve these integrated constraints by diagonalizing the perturbation Hamiltonian. I'm not going through the entire process, but let me try and explain just this, what this solution means. It states that the solutions of this integrated constraints can be written in terms of a Fock space wave functional, which is depending on the matter sector and the physical gravitons. And it is entangled with the value of the energy at the boundary, which in the case of ADS takes on discrete energy eigenvalues. And these Fock space wave functionals can be constructed by acting with ladder operators on the ground state wave functionals, which are our familiar Gaussian wave functions. Okay, now the important point is that these constraints show us how the dynamical degree of the wave functions are correlated with the value of the boundary Hamiltonian or the energy. You could also solve the pointwise constraints. It can be written in this form, at least up to order kappa. But it's not very illuminating right now, although it's very interesting in its own right, and therefore I'm not going to talk more about this. And I just want to remind you all that we are still working with solutions within perturbation theory. Okay, now just to again recap what the statement of holography was, and to prove it in one slide, we can in general consider any density matrix which looks like some arbitrary coefficients times psi star psi, where these coefficients would tell you what the density matrix are.
Chandra, sorry, can you wrap up in a couple of minutes?
I'll wrap up in 1 minute.
Okay, thanks.
Okay, thank you. These A's just denote the degeneracy. Like you could have other labels of the other things labeling the state. So these coefficients tell you the density matrix, and psi star psi the usual expansions in terms of energy eigenkets. And again, if you impose such a the equality of such correlation functions with these O's being the boundary operators, either scalar or graviton or something else, and H boundary being the energy, then you would be forced to have C1 equal to C2. I'm not going to go through the full proof, but in general, after skipping some steps, you can actually say that you can actually look at the difference of these two correlators, and they take some following form. And then you can argue that such correlators of O's are non-zero using the edge of the wedge theorem, with which forces C1 equal to C2. Okay, so to wrap up, what we've shown is that if you have two wave functionals which solve the Wheeler-DeWitt equation in ADS, and they coincide near the boundary on an infinitesimal time interval, then they coincide everywhere else. This thing was done in perturbation theory. You'd also mentioned that the correlators that we're measuring are not necessarily going to give you real answers. You can also look for physical protocols which will do the same. And there are some natural extensions. Everything that I've done can be easily done in D greater than equal to 4, but ADS2 and ADS3 are perhaps harder stories. And similarly, you can ask more questions about black holes, flat space, de Sitter, or entanglement wedge reconstruction, and so on. Thank you.
Okay, let's thank Chandramouli for a very nice talk. We have a couple of minutes maybe for questions. Let's see, I don't see any. I don't see any hand.
Okay.
Chandramouli, maybe I can ask a small question. So what happened to the diffeomorphism constraint? You just gauge fixed it, is it? In the
You mean the moment?
Momentum constraint, yes.
Yeah, I could have also looked at solutions of the momentum constraint.
Yeah.
And then try to construct this. But in order to run this argument with edge of the wedge theorem, it's typically better to run with energies as they're positive. With the momentum constraint, I would have gotten some constraint on the angular momentum, which could be positive or negative. And that would not allow me to run this argument in a very nice manner. So it's better to just consider these energy eigenstates instead of that.
But you must have either gauge fixed or solved the momentum constraint, right? When you wrote the physical wave function. So like your shift vector somehow disappeared. That's how.
Oh yeah. I mean, this S in here does contain HL and HT. Like that does contain HL as well.
Okay, nice.
So this S contains everything. Yeah.
Thank you. Okay, then let's thank Chandramouli once again.